Hi, it's Ryan. This will be a short video showing an example where we use the magnetic force law, but with respect to a current carrying wire in an external magnetic field. So I, L cross B. The problem statement is given as determine the current required to make a 20-meter long copper wire levitate above the equator. Also determine the direction of the current. So we're going to draw a picture, and there probably would be a little more given in the problem statement if you were working on this on, say, a quiz or a test or something. So that'll be the Earth, and what we're kind of doing is looking at the south pole of the Earth. So the reason being that the magnetic field goes from south to north, as shown in class the other day. So I'm just going to show the Earth's magnetic field sort of going into our page, going from south to north. That's B of the Earth. And we actually know B for the Earth is 0.5 Gauss. We know L for the wire is 20 meters. And that's about it. It also should probably give the mass of our wire. The mass would be, I don't know, let's say 5 kilograms. Anyway, I'm also going to draw the wire in. There it is, and I have it levitating above the equator. And maybe we could also, just to remind ourselves what's going on, we could show an FBD for the wire. In order to be levitating, of course, its weight force must be have an equal and opposite force so that it can be floating and not accelerating in any direction. And that equal and opposite force would be the magnetic force on the current carrying wire due to the Earth's magnetic field. And so I'm going to show that force on our picture. And now maybe we could try to determine what direction the current has to be in order to create a magnetic force going upward on that wire. So I'm going to show I1 and I2. It could be going one of two ways. And now what you should do is do the right-hand rule number 1, where you point your fingers in the direction of one of the currents, curl in the direction of the B field, and your thumb should be giving you a magnetic force direction that's pointed up in the end. So if I were to try this, if I were to point my fingers in the direction of I1, let's say, point my fingers in this direction, and then curl them into the page with my right hand, I think that would yield a magnetic force going down. So the point is, you should be able to show using the right hand rule, I2, which is going, if we're looking from south to north, I2 would be going east. Will create an upward magnetic force. And we can even note using right hand rule number 1. So we've actually sort of answered this part of the question. Now, using the magnetic force equation, we can try to determine the magnitude of that force. FB, the magnitude of any magnetic force, is always, well, it's not QVB here, it's ILB. and sine phi, where phi is the angle between the direction of the current and the magnetic field. Well, in our case, it looks like they're perpendicular or orthogonal to each other. If the magnetic field line is going into the page and I2 is going to the right, then you can kind of imagine looking from this part and seeing them at 90 degrees. Well, if phi is 90 degrees, then the sine of 90 is, of course, 1. And so FB's magnitude will be ILB. But this is asking for I, isn't it? Well, looking back at the FBD, we can see that because there's no acceleration, the sum of our forces is 0, which will yield that FB is simply equal to the weight of the wire. And so we can go ahead and substitute mg in for FB, and we can solve for I. And I think we have all the information to actually calculate this value. And I think you'll see it's a very large current that would be required in such a relatively weak magnetic field. But there you have it.